So, as I was saying, what if the core becomes partially degenerate? And basically what will happen is that in this entire expression P of isothermal core, another term will be added because of this partial degeneracy. Now I am not saying complete degeneracy. Core becomes partially degenerate. Now as a result of this partially degeneracy, what will happen is that only the internal energy term will change. Now to understand this, let us first write the expression for pressure. So now the pressure expression or equation of state will be due to the ideal gas along with your non-relativistic degenerate gas, right? So two expressions, ideal gas, non-relativistic degenerate gas. Now this is quite normal to you, you know this, K in R root to the power 5 by 3. Now what I have done, I have separated out the part of mu E out of it, the electron contribution out of it, and as a result I have written it like in this form. So this is the equation of state. And now in the virial theorem part that we derived in the last part, so there were three terms. The second term was the internal energy contribution. So now I am going to again see how the internal energy changes as a result. So again P by rho, because the pressure was there in the internal energy. So P by rho, so I am again writing this using this term, and as a result I have got this integral. Now again I am going to use the dimensional analysis and I am going to write this in this form. So I am breaking this density in mass and then using the approximate dimensional relation to get this form. Now this is an alpha. This alpha is a constant basically which depends on the mass distribution of the isothermal core. Okay, so what we will do next is we will now use this result, we will put this part. So this is the new part due to partial degeneracy. So we will put this part into our pressure term due to isothermal core, and we have got a third term over there. Fine. Next দেখো যেটা করলাম এই পুরো জিনিসটাকে এবার আমি in terms of RIC লিখেছি. Okay, and you see that this you can write in this form, and I am just ending today's lecture by saying that at this critical value of mass the two turning points will coincide at an inflection point. Now before I tell you the meaning of this part, I would like you to at least check this calculation and you will understand yourself what I mean by that. বুঝতে পারছো? এই ক্যালকুলেশন একবার চেক করো, মানে এখন বলছি না, বাড়িতে গিয়ে একবার চেক করবে যে এটা সত্যিই ঠিক আছে কিনা। And is this critical mass same that we have used previously or not? And what is the consequence because of these two different critical masses? বুঝতে পারছো? এইখানে যেটা আছে মাস ক্রিটিক্যাল and previously isothermal core সময় যেটা করেছিলাম maximum mass Q critical থেকে, are they the same or not? And if they are different, what is the consequence of this? This I will talk about in the next class.
So we have derived this previously, and this third term is due to the effect of the partial degeneracy. Fine. Now you see, as a function of RIC, this pressure has now two turning points. So let me write this down. What the turning points are. And this is what you get. So you see there are two values of RIC for plus and minus, two values. And what this means is the following. Let me show you on the graph. Okay, so now you see this term concentrate. Now I can write this entire term over here as a mass, as some mass, some critical mass, m critical to the power 4 by 3. I can write. Let me show it to you. So basically, if I do that, then what I will get from this term is the following. I will get from this bracket 1 minus m critical divided by mic whole to the power 4 by 3, and of course there is this small over there, right? 1 plus minus and then the big bracket. So this I can write as the m critical. So what is the value of the m critical? So this is the value of the m critical, and you see the corresponding graph, pressure as a function of this radius r I have shown over here. You see what is happening is that at this critical value, so at m critical, two turning points, they coincide at an inflection point. Now you see, for higher masses there are two turning points. So higher masses means this case here, mass greater than m critical. You see this case, there are two turning points here and here. But for lower masses, this one, there are no turning points. No turning point. Let me okay, no turning point, and here two turning points. So this is for higher mass, this case, and this is for lower mass. Now you see, at core temperatures, at TICs of the order of 2 into say 10 to the power 7 Kelvin, the critical mass m critical, it is of the order of 0.1 times of the solar mass for reasonable values of alpha. Now here, for this case, for this particular case, we have shown this plot. It is important to remember. Now what you can understand from this plot is the following. You see, when hydrogen burning stops in the core and Q is less than Q critical, then the isothermal core can support the envelope, right? And the pressure and radius are given by a point on this curve over here, appropriate for the envelope pressure given by Q. Now while hydrogen burning continues in a shell around the core, the mass ratio increases. Now what will happen? You see, an increasing mass ratio will cause this curve to move to that defined by higher core masses, right? Now if the core mass, you see, if this core mass never exceeds the m critical value, then the core smoothly transitions. Here there is a smooth transition from this ideal gas region to the degenerate gas region. However, if the core mass eventually exceeds the m critical value, then as the mass ratio increases, it will reach this Q critical, and at that point in the star's evolution there is no stable solution and the core will collapse, you see, towards the degenerate solution as the temperature rises. Okay, so what you can understand here is basically the steep rise. The steep rise in this pressure at small radius, this is due to increasing degeneracy of the core gas. This steep rise. steep rise due to increasing degeneracy of core gas, right? And you see the star, it basically starts at a point on the curve at very large radii. So star starts at large r from here, and then it slowly progresses depending on its mass. Now you see, as the star starts, its Q increases. You see from here, the Q increases and the star moves up the curve. And here we have got two paths. So this path is basically for no turning points, means basically MIC is here less than your M critical. And here, in the other hand, this case is basically MIC greater than your M critical, as you can also see from here. Now, in this case, Q will eventually reach Q critical and the core will rapidly collapse. See? So, this is what I mean by saying the collapse. The collapse is happening over here. You see, pressure all of a sudden decreases, whereas the radius increases. But after that, slowly, the steep rise is due to the increase in degeneracy of the core gas, right? So, basically, this is where you can say the collapse happens. Collapse is happening. Okay. Now you must be wondering which stars do this case belong to. So basically this case belongs to stars with mass greater than equal to 3 solar masses, since for them this isothermal core mass has value larger than the M critical. Okay. Now let us follow let us follow the evolution of a high mass star with shell hydrogen burning around an isothermal what core? Helium core, right? Now you see this shell burning, basically as a result of this shell hydrogen burning, what will happen is that the core mass will increase, core mass basically will increase, and this will happen until Q exceeds Q critical, and then core can no longer support envelope. Right. Now what will happen is basically the collapse, and so collapse of core happens, and this, remember, this occurs at thermal time scale. Right. So let me give you a value. For typical core values, say of the order of 0.1 solar mass and this radius of core of the order of 0.3 solar radius, this thermal time scale is of the order of 10 to the power 6 years only. In the stellar time, this is not very large. Now in this case, you see the energy conservation and virial theorem. Energy conservation and virial theorem, they required that the gravitational potential energy and internal energy, which is U, and gravitational potential energy, they conserved separately. Okay. Now you see the self energy of the core is substantially greater than the self energy of the envelope due to smaller size and greater density of the core. You see, the self energy of core is greater than the self energy of envelope due to smaller size and greater density of core. And so we can approximate the total potential energy of the star as the self energy of the core plus the potential energy of the envelope. So let me write it down. So we will approximate the total, basically this total potential energy of star, total potential energy of star, as you see the self energy of the core and self energy of the core and the potential energy of the envelope due to gravitational contraction of the core. So let me write it down. Divided by R, and so this is basically self energy of core, and this one is basically the potential energy of envelope due to gravitational contraction of core. And we have basically ignored the self energy of envelope since it is smaller than that of the core. Now you see this is approximately constant here, and this R is the radius of the star. Now you see during the relatively rapid collapse of the core, the shell burning does not have time to appreciably add to the mass of the core. And so we can treat this MIC and M envelope as constants. Let me write it down. Now, so this R is radius of star. And so what I was saying is this: during rapid collapse of core, shell burning does not have time to appreciably add to mass of core, and so we can treat MIC and M envelope as constants. Fine. Now let's see what happens. So now you see conservation of omega of this gravitational potential of this, then potential energy, then gives us you see this value. And so from here what we have is this result. This value. So basically the radius of the star, it increases as the core contracts, negative sign. So this means radius of star increases as the core contracts, right? Now during this phase, the matter below the hydrogen shell, burning shell, is collapsing while the matter above is expanding, right? So it is like this. Oh, this is not okay. Sorry, this is not okay. Yeah. Yes, this is not. Yeah. Let me write it. Yeah. So this envelope is expanding outward, and this core is rapidly collapsing inward. Now this stage where the bulk of the luminosity arises from the collapse of the core happens quickly, as I have just shown you previously. The time scale is of the order of thermal time scale 10 to the power 6 years, right? And so it is rare to observe stars at this point in the evolution of the main sequence over to the red giant phase. And this region of the HR diagram is known as Hertzsprung gap. Okay. Now you see, as the envelope expands and cools, eventually what will happen is that the temperature will drop to the point that H negative ions can be formed. T decreases and later on H negative ions can form, and then they start contributing to opacity. Now this increased opacity results in development of convective core. Remember, in the convective stars section I have talked about. So development of the convective zone in outer atmosphere. I have talked about this. Right. Now the star continues to expand and cool due to the collapsing core, and so its effective temperature and luminosity follow a Hayashi track, but in the reverse direction from a collapsing protostar. Let me show you. Okay, maybe I will later show this to you. Anyway, so as a result of this, what happens is that effective luminosity and temperature follow a Hayashi track, but in reverse direction and from a collapsing protostar. Thus, you see, the luminosity increases substantially while the effective temperature remains fairly constant. Luminosity increases while T effective fairly constant. It remains. While T effective it remains constant. Now at this point the star is basically a red giant. Okay, and this is a red giant. And the convective zone, you see, can reach all the way down to the hydrogen burning shell and transport materials enriched in metals from the nuclear burning in the shell up to the surface. And this process is known as dredge-up. Okay, this is important. Dredge-up. Now the core remains non-degenerate during the collapse, and as the temperature in the core increases, you see it eventually reaches the ignition temperature for the triple alpha process, helium burning, and this happens at around, so eventually T increases, what's the value of the order of 10 to the power 8 Kelvin. So triple alpha, 3 alpha process begins and the contraction of the core halts. Contraction of core halts. And the star settles in again. So star settles in what? Thermal equilibrium and again hydrostatic equilibrium. Now you see the core will slightly expand and the envelope will contract as a result. Expand and envelope contract. Okay, so you see at this point the star now consists of a helium burning core surrounded by a hydrogen shell burning. As the helium burning proceeds, so this point basically helium burning core and outside hydrogen burning shell, and then we have the big envelope. So this is what is happening at this point. Now as the helium burning proceeds, you see the mean molecular weight again increases in the core. Why? You see, as 3 helium nuclei are combined to form 1 carbon nucleus. Now this change is not as dramatic as for hydrogen burning, but the core does contract slightly and the luminosity increases. So during this helium burning stage, you see the convective region in this envelope, it shrinks. Here the convective region, whatever was there, it basically shrinks to the surface. But the high temperature dependence of the triple alpha process, it causes a convective zone, convective core to develop again. Now stars burning helium in their cores occupy a region. So stars burning helium in core, they occupy a region in HR diagram which is known as horizontal branch. Okay, and you see stars proceed through this horizontal branch on nuclear time scale, and so they are frequently seen. They can be seen. Eventually what will happen is that a carbon core develops with the helium shell burning. So eventually we will have a carbon core and helium shell burning. Again there is a hydrogen shell burning outside and then your envelope. And so basically we have the contracting core surrounded by the two burning shells, right? And the envelope expands and the luminosity drops. So you see the evolution is now similar to the evolution towards the red giant phase, except that there are now two shells of burning, hydrogen and helium. Now a convective envelope develops and there is a second dredge-up. So remember I talked about dredge-up. So dredge-up is basically when due to convection, so dredge-up. Dredge-up is basically when due to convection there is mixing in the materials. Now there are two dredge-ups, first and second. In the first dredge-up we have only helium core plus hydrogen shell burning, and helium core was not burning, right? So this was the first dredge-up. In the case of second dredge-up, we have carbon core and plus two shells, hydrogen and helium, and they are both burning, right? So remember there are two types of two dredge-ups. Okay. So this is the reason for the second dredge-up. Now you see the star again follows the Hayashi track again. So in this case the star again follows Hayashi track along what is known as asymptotic giant branch. Okay, AGB. Now let me show this to you in graphs. Finally, all the words and after that graph. So here you see I have shown you the actual three branches, the red giant branch, horizontal branch and the asymptotic branch for this cluster M5. So these are actual giant branches. For this cluster M5. Okay, and you see this I have shown you schematically in an evolved cluster. So basically what you can see here, the first is the red giant branch. What is this? Basically here you see the core contraction happens with hydrogen shell burning, and this leads to the triple alpha ignition, and deep convective envelope and surface mass is lost. Convective envelope is there and surface mass loses. We lose that, and I will talk about helium flash later on. It can also happen if the mass is less than 3 solar masses. Now in the case of horizontal branch, basically here we have the core helium burning scenario. Remember this period is much shorter than for hydrogen main sequence because there is of course less helium as well. One of the reasons. Other reason you find it out. We will discuss in class. Anyway, and then we have this asymptotic giant branch where the central helium is consumed and thus leaving the carbon oxygen core. And you see this interacting. So we have two shell sources here, hydrogen and helium, and in this case element production is possible by the slow process, S process. Okay, next I am going to show you this calculated evolution of a 5 solar masses star. You see everything begins at the ZAMS when the star converts hydrogen to helium, and this causes a very small upward drift on this HR diagram, right? Of course the luminosity will increase due to core hydrogen burning, And you see, as hydrogen is depleted, the core contracts here. This is that core contraction phase. Remember, we discussed the Schoenberg-Chandrasekhar limit in this regard. And eventually, a hydrogen shell source is established over here. It is important to note that these events basically signal the advent of a rapid departure from the main sequence. Okay, now we will be moving away from the main sequence. Now you see, the hydrogen shell source that we have established, that has been established, when the core hydrogen is depleted, it burns outward, leaving behind a helium-rich ash. And we remember the Chandrasekhar-Schoenberg limit, M critical by total mass is of the order of 0.37 times the square of mu envelope by mu of the isothermal core. So basically, the growth of an isothermal helium core to this size, it typically requires, for reaching this limit, around 10% of the original hydrogen to be burned. Okay. And you see, when this Schoenberg-Chandrasekhar limit is reached, the core can no longer support itself and or the layers against gravity, and so the collapse happens. And this happens on a Kelvin-Helmholtz time scale. You see, so basically the collapse will continue, right, until the ignition of helium fusion in the core provides a stabilized pressure, or you can say until the interior densities are reached where the electron gas becomes degenerate. Now you see, the provided that the core mass does not exceed around 1.4 stellar masses, the degeneracy pressure, it stops the collapse. But only after the core has become much hotter and denser, and substantial gravitational energy has been released. Now remember that much of the energy released in the collapse is deposited in the envelope, which expands and cools, enlarging and reddening the photosphere. Thus you see, the star evolves rapidly upward and to the right over here, this direction, relative to the main sequence, into the red giant region of the HR diagram over here. So basically what I am saying is the movement over this direction in this part. Okay, so this is what I am saying. You see, the region between the main sequence and the red giant, roughly between these points 5 and 6 over here, this contains very few stars, and that's why it is called a Hertzsprung gap. Very few stars can be observed. Remember the time scale, 10 to the power 6 years we talked about. Now you see, the star evolves so rapidly through this region that what happens is that there is a little chance of observing it in the Hertzsprung gap. Now as the envelope temperature decreases, opacity increases and the temperature gradient exceeds the adiabatic gradient. And what happens? The star becomes convective in much of its envelope. Okay, and so a deep convective envelope develops. So you can say that we may see it like this, that the evolution to the red giant region is basically like the inverse of the collapse of fully convective protostar to the main sequence. The protostars were collapsing along this, but now we are going in the reverse direction. Now this almost fully convective star climbs the Hayashi track, but in the reverse direction to the red giant region. Okay, so here inverse, moving inversely, reversely in Hayashi tract. Okay. Now, while on the red giant branch over here, you see the greatly expanded star can exhibit significant envelope mass loss. This can be very large, around 10 to the power minus 6 times the solar mass. But remember, the temperature will be very high and triple alpha reaction can start as soon as your temperature reaches around. So this happens when T increases around 0.8 into 10 to the power 8 Kelvin. Now you see the onset of the helium burning. It corresponds to this cusp over here, and it signals the end of the red giant branch evolution. So red giant branch ends. Okay. Now you see this ignition of the core helium burning is different for stars above and below 3 solar masses. Core helium burning is different if mass is less than 3 solar mass and if it is greater than 3 solar mass. Again, so there is a limit or so. So what happens is that, you see, for stars of around say 6 solar masses or more, they have enough central temperature to evolve all the way to helium burning without their cores becoming degenerate. And under these conditions, the commencement of the core helium burning is probably a rather smooth and orderly process. However, you see, for stars around 3 solar masses or less, the core electrons will have become highly degenerate even before the triple alpha sequence ignites. It is possibility. It happens, actually calculations have shown this. And we know that the equation of state of the ideal gas and degenerate gas, they differ fundamentally in their relationship between temperature and pressure, right? For ideal gas, the pressure is proportional to temperature, whereas for degenerate gas, the pressure is essentially independent of the temperature. Now, the ignition of this, you see, the thermonuclear reactions under degenerate conditions, it actually leads to very violent energy release. So, what happens is that this ignition of the fusion reaction, it basically releases large amount of energy, and this quickly rises the local temperature. Now in a normal explosion, say in an ideal gas, a rise in temperature causes a corresponding rise in pressure. So that separates and cools the reactants, and this limits the explosion. But in a degenerate gas, because pressure is not increased initially by sharp temperature rise, this will not happen. Now remember that charged particle fusion reactions have very strong temperature dependence, and so the rise in temperature causes a rapid increase in the reaction rate and the fusion reactions run faster, and this in turn raises the temperature further and thus reaction rates, and this goes on. So basically we have got a thermonuclear runaway. Now the large thermal conductivity of degenerate matter means a thermonuclear runaway triggered locally will what? It will spread very rapidly through the degenerate matter, and this runaway continues until enough electrons are excited to lift the degeneracy of the electron gas. Okay, and the equation of state then tends to be that of an ideal gas, and the resulting increase of pressure and the temperature moderates the reactions. Again, the secular thermal equilibrium scenario will happen. Okay, now, so you see, when such a thermonuclear runaway occurs under degenerate conditions for the triple alpha process, it is known as helium flash. Fine. You remember, I have already talked about it when I was discussing the sun and its helium burning scenarios in the class. So, once the degeneracy of the core is lifted following the helium flash, so basically, so here we have a possibility of helium flash over here, and once the degeneracy is lifted, then the helium burning steadily proceeds to carbon, right? And this signals the beginning of the horizontal branch. So this is the horizontal branch, remember? Here, this is the horizontal branch, and here this is the horizontal branch. Okay. Do note that this horizontal branch basically, so this is the red giant branch, this is the horizontal branch, horizontal giant branch, and remember that this corresponds to a period of stable core helium burning, and it is very similar to that of the core hydrogen burning main sequence, right? And so this is also known as helium main sequence, helium main sequence, and there we have hydrogen main sequence. Remember these things. So we can have helium main sequence here because of this similarity between stable hydrogen burning here and stable helium burning over here, right? Now this helium burning main sequence is a time of hydrostatic equilibrium for the same reasons as for the hydrogen burning main sequence. However, do note that this helium burning main sequence is much shorter than the hydrogen burning main sequence, right? Remember the burning time scale scenarios. Now initially on the horizontal branch, the star typically has lower luminosity than in the preceding red RGB branch, but higher than what it was on the main sequence. Okay, now you see the star remains on the horizontal branch as long as there is helium fuel in its core to burn, and when the helium core is exhausted, the core contracts and thick helium burning shell is established. Okay, and then the star has two shell sources, the broader helium burning shell and the thin hydrogen burning shell. Now remember our mirror principle. So because of this, what will happen? So see here. So basically the mirror principle. Now you see what will happen is that the inner core inside the helium source, it will contract since there is no power source. However, the inert helium layer, this one, helium layer, outside this helium shell source expands, and what happens is that it pushes the hydrogen shell source to larger radii, and the outer layers of the star, they contract. Okay, and this causes the star to move left in the HR diagram. Over here, see this part. So this part, move left of the HR diagram between points this and this. Now you see the helium shell source narrows and strengthens as the core compresses further, and layers above the helium shell source expand and cool, which turns off the hydrogen shell source that was burning above the helium shell source, leaving what? Only a single active shell source, which is helium. Okay. Now in accordance with the Meyer principle, then what will happen? The star contracts inside the helium source and expands outside, and drifting quickly again to the right side. Here, like this, similar to this case, until it reaches the vicinity of this Hayashi point, Hayashi track. And this signals the transition to the asymptotic giant branch. Okay, this signals. So in many ways you can say that the evolution on this asymptotic giant branch basically mimics what follows the establishment of the first hydrogen shell source after the core hydrogen was depleted on the main sequence. However, do remember that now the star has an electron degenerate carbon oxygen core and two shell sources instead of only one. So remember, right? Also that the hydrogen source is turned off after ignition of the helium shell source, but it will reignite after early evolution on the asymptotic giant branch. And the star again increases in luminosity and radius and moves onto the red giant region as earlier, but at even higher luminosities on the asymptotic giant branch. Okay, and this corresponds to the evolution along this. So roughly the continuation of the ascension on the RGB along the Hayashi track that was uninterrupted by ignition of the core helium source that destabilized the star for a time on the horizontal branch. Now if you see the star is massive enough, the growing carbon core may ignite eventually, but if the mass is between 4 to 5 solar masses, then this is not likely, and all subsequent energy production will be from the shell sources.